And here we are in the lab again, and this is episode 2 of MainBrain. Build yourself your own MainBrain. Okay, so in the last video, we got an idea of what MainBrain is and kind of how it's made up and stuff. So this one, we're going to start going through the modules. So this video is on the power supply. Because that's, originally I said we were going to do the microcontroller first. And I know everybody wants to see that. But the way we put the parts on the board is we build the power supply first. And then when the power is, everything is good, then we put the microcontroller on there. So we're going to do the power supply now. And then after the power supply is done, then we'll do the microcontroller. And we're just going to do the hardware right now. We'll go through the whole board, each module's hardware, how it's made, little details, this and that. And then we'll go back around at the beginning and we'll start putting parts on the board and taking measurements and discussing this and that and how to do it. And you'll see some soldering techniques and stuff like that. So right now, let's go to the power supply. Oh, and there's something I hadn't mentioned yet. So it's the form factor of MainBrain, and that's the size of the board. And there's a little bit of history here because in the early days, I didn't know about PCBWay, and I'm not sure how long they've been available, but I used Express PCB, I believe. And so for the prototype size at that time, it was like, I think 2.5 by 3.5 inches. And so that's how and that's what I used. And it was like $80 from them guys, you know. And now PCBWay, it's like, even with shipping and everything from China, it's like $40. And a lot better quality too. But that's how the form factor, the size of MainBrain got started. So I just stuck with that. That's a good, it's a good challenge to keep everything you want to do with a board in that size. So the form factor is approximately 65 millimeters by 95 millimeters. So let's take a look at the form factor. Okay, so here is the exact dimensions of the board, like you'll see in the Fusion files and stuff like that. This is the official size of MainBrain. And then the holes are required to be exactly like this. And as you'll see, the holes are 4 millimeters. So that should be big enough to put a screw in to mount it about anything you want. Gives a little extra size for if you use 3 millimeter screws. It gives a little extra hole space for a little ridge, a registration point on your offsets to fit in the hole without sliding around, a little indexing. And so the dimensions are in millimeters, and they're not even because they're translated from inches, but that's the official form factor of MainBrain. So that's the official form factor of MainBrain, but you can make at any size you want. You can make like a lot of additional I/O boards that we are going to make, and like the I/O board and the other video and the motion board. You can put that all on one big board in modules, however you want to do it. But to actual follow the project, that's the official form factor of MainBrain. Okay, so now for the power supply. So MainBrain uses an onboard switch mode power supply. And so technically, since it is bringing in a DC voltage and puts out a DC voltage, then it's a DC to DC converter. And more specifically, it is a buck regulator or a buck converter, which means that it takes a higher voltage and it chops it down to a lower voltage. So Why switch mode? Because I originally I tried a linear regulator. So you just buy one of those 3-pin TO220 package devices, you stick it on the board, you put a couple caps on it, they cost about $2. Uh, you run in say 9 volts and it outputs 3.3. It's all great. But then when you stick 24 volts onto it, or 30, usually they go up to 35, but you put a 3 amp load on there, and even though you have it bolted to the board good and you put 24 volts on it, that thing is gonna start cooking. It gets, because a linear regulator acts as basically like a resistor. It takes all that voltage that you're not using. So like if you have 24 volts and you're stepping it down to 3.3 volts, then you got like 21 volts right there about that you have to like get rid of. And so a linear regulator has to get rid of that in heat. So if you're going from 9 to 3 or 5 to 3, you could go down to 5 pretty easy on a linear. So you could put 5 volts in, 3.3 volts out. Everybody's happy, right? Cheap, reliable, works great, no noise, no problem. But you stick 24 volts on there, it's going to get so hot, it's going to be unmanageable. You probably can't. You'd have to have a heat sink like this big. And you don't have any room to spare on MainBrain. I mean, there's no room to spare. So anything you can do to get it down there into a smaller package, you got to do it. And switch mode can do this. It takes about as much area as a quarter. It costs under $10 for sure, maybe or closer to 5, depends. But so it can put out higher current. So that's MainBrain puts out 3 amps easily. It don't care. 3 amps, it loves it, right? And so it can put in 24 volts all day long. Doesn't really get that hot. It does get a little bit of heat built up, but it's the switch modes is the way to go if you can do it. The only problem with that is they're more complicated, more complex, more expensive. But this circuit is fairly simple. It seems very reliable. And when you put it on the board, if you get everything, all the parts for it on there, and you plug it in, 90% of the time it works. If it doesn't work, it's because you messed up somewhere. And so I went with that, and I'm sticking with it. It is really good. But originally, I used a different chip because I wasn't thinking about 24 volts, because I just was making a microcontroller. So, hey, 12 volts is great. So I used a 23 volt chip and it worked great. But then I realized when I started messing with the motors and the motion boards that a lot of systems out there use 24 volts. The motor used 24 volts. So why not use the same power supply for everything? So then I changed it to this chip now. And so we can put in 24 volts and between 7 and 24 volts DC. And you just plug it in. You don't have to worry about it. And it works really good so far. And it's been running. I've ran these, like I leave them on all the time. And I load test them and stuff like that. And everything seems good. And so let's take a little deeper dive into how this power supply works. So here's a diagram of a buck converter. And so it's simplified, obviously, but basically how it works, I'm not going to get into the theory and everything. You guys can study that on your own, and some of you already know. So the E is the voltage coming in, and it goes through the switch S, which is usually a MOSFET. And the MOSFET is usually controlled by a PWM controller that gets feedback. It measures the voltage output, and so it gives feedback so that the voltage output always stays within specification. So it pretty much chops. People think about converters as just chopping the voltage. So the more time you're on, the higher the voltage. The more time you're off, the lower the voltage. So the switch opens and closes really fast in real life, but it does in a manner that regulates the output to the voltage that you want. So it's kind of like charging, and then it allows to discharge through the load. Then it charges it again. So it's just turning on and off real fast. And the capacitor, the inductor helps the charge. That's the flyback that actually makes the charge. And because you have to have a changing magnetic field, blah, blah, blah. But C, the capacitor smooths out the ripple caused by the on and off transitions of S. So you get a smooth voltage out to the load R. And that's basically what we're doing. Okay, so that's how a buck converter works. That's the basics of what that's what we're doing on our power supply. So, and so in the late 90s, I worked for a company called Storage Technology Corporation. It later got bought by Sun Microsystems, and they tore the whole place down and moved it away. The only thing there now is like concrete pads. It was in Louisville, Colorado, right next door to Boulder, Colorado, right down the road. But and so we built power supplies there for disk arrays, for storage arrays. And so I got a lot of experience with power supplies and stuff like that, but I'm not a power supply engineer by any means. So there's a lot of little tricks with the PCB and noise coupling and stuff like that, and resonant frequencies and stuff that go on inside these switch mode power supplies. And so I'm trying to get my board as low noise as possible. Now the ripple coming out is pretty good. I mean, it's down pretty low, but like where I measure the current and the voltage with the 80 converter, it gets a little noisy because we're measuring millivolts. So some of the switching frequencies get coupled through there. That's why I added some of those caps. But it's an unsophisticated way of getting past the problem. And I don't know all the finer details of the design stuff like that. So this is where you guys out there can come in and say, hey, this is like a little bit over too close or something. Something that I missed, you guys call me out, and because I'm not like trying to say I know everything about it. So, and in that section in power supply noise and stuff, I'm kind of on the lower end. So you guys got to help me out. When you see something wrong or something that could be better, let me know, because I will really value that input. So now let's take a look at the schematic of our power supply. And this is the schematic here. So over here is our input jack. So we can put in 7 to 24 volts DC. That's the recommended voltage range. All right, I tried to go down to 5. 5 doesn't work because by the time it goes through the diode and all that stuff, it apparently isn't enough voltage to give it enough headroom to do the 3.3 volts out. So starts out, the voltage goes in here in our jack. It goes through a diode, which is just to protect it from hooking up the power supply backwards, reverse polarity protection. And then we got a capacitor and a filter here. And this is new. So I haven't seen the results of this filter yet, so we'll see that together. But that is to keep a lot of the noise from getting back onto the supply, which isn't really that big a deal at home, but in other circumstances, maybe you don't want that. So I'm trying to cut that down as much as possible. There's a lot of ways in here to get coupling from the switching noise. So noise is a factor here. So then the next thing, it goes through a filter cap, and then right here we have a voltage divider and a cap, and this cap just acts as an RC filter to cut some of the switching noise off of this line, because this is a sense line that senses the input voltage, and it goes into the AD converter of the microcontroller. So that's where you see that on the Windows app. It gets the voltage senses from here. All right. And so then next it goes through some more filter capacitors, kind of like a bulk capacitor at the same time too. Keep the voltage stable from any load fluctuations and stuff like that, switching fluctuations. And then here we have a compensation for the regulation loop internal to the switching chip. And then this is the current limit setting right here. So this IC, if it gets loaded more than this 3 amp rating, it will just shut down. And it won't start until the excessive load is removed, like a short or excessive load. All right. And also, if it gets too hot, it will shut down and won't start until it goes below its threshold. All right. So it's fairly protected. You can't really blow it up under normal circumstances. I have a feedback loop so that it can regulate. And this voltage divider here sets the output voltage, in our case 3.3 volts. And then we have a 100K here that enables it. So as long as when there's an input voltage, then it will start the chip. You can also have a microcontroller turn this on and off if you wish. And so then this is our main inductor here, where the flyback, where it does the switching on the inductor. That's the heart of the switch mode power supply. And so then it comes out, and it's pretty much right here. It's 3.3 volts. We got 2 capacitors right here, low ESR capacitors, and that's required by the spec of the chip. And so everything past here is mostly for the microcontroller stuff. The voltage is good right here, pretty much. So we come in here and we go through a 100 milliohm resistor, and that is a voltage sense, or current sense rather. All right, so it senses the voltage drop across here, across this resistor, and makes a calculation. And this 2.49K resistor is what sets the ratio. So with this in there, it's 1 millivolt equals 1 milliamp. All right. So then we have another cap here, a 1 microfarad cap, and that is a filter that acts as with this resistor as an RC filter to cut the noise down off this iSense, because that also goes into another channel of the AD converter of the microcontroller. And then we have what they call a decade set of capacitors. So each one is a factor of 10 different from each other. So it's to filter out high frequency noise. So you got a 0.01, a 0.1, and a 1 microfarad cap. All right, so then finally we have an indicator, a power on indicator. So when the power supply is putting out voltage, then you will get this LED will light up. All right. Okay, so that's the schematic. That's the official schematic that I have in Fusion 360 that I will be putting on the website, and I'll have a link up in here in the description of the video for my website where I keep the public versions of everything. And so to wrap things up, we'll look at the data sheet for the power supply chip and just go over that real fast, and that'll wrap up this video, and then we can move on to the next one. So let's take a look at the data sheet. Okay, so here's the data sheet for the power supply chip. It's made by Rich Tech. It's an RT6283B. And it's basically 3 amps. And you can program it to put out whatever voltage you want. It runs on 30 volts down. So MainBrain is recommended to run between 7 and 24 volts, but you can go to 30. That's pushing the limit. I don't know how far above 30 you could go. In the old days, I had a 23 volt chip, and I tried to put 24 on it, and with the drop of the diode, it was just right on the edge, and you could get away with it in some circumstances, and in some circumstances it would freak out and do damage. So if you want to go above 24 volts, it's heading towards the danger zone. I feel good about having some cushion between that 30 volts and what I'm using. So what else? It switches at 500 kilohertz. So that's a factor in noise whenever you want to make a filter or something like that. And so the output can go from 0.8 volts to 24 volts output with a 30 volt input. All right. All right. And then it has some features there. This is how we hook it up. And that's pretty much the MainBrain circuit is pretty much like that. So this is the package. It has a ground on the bottom of it that you have to solder on the board. And that is for a heat sink and also some noise stuff and performance, but it keeps it cool. It keeps it cool when you load it to its rated current. This is what it looks like internally. I'm not going to really go through that. You guys can study that yourselves. That's not really the scope of what we're doing here. And then this tells about what the different stuff does in there. And then here's the maximum ratings. It's like you should always look at the data sheets for that kind of thing when you're building projects. So then this is the application circuit. And that's pretty much what we have. And it gives you the values of things here that you should use to get whatever voltage that you want. And so then we have 3.3 here. So we have these guys in there. And then there's some operating characteristics and stuff you can look at. And this is how the different things work, the chip enable, how you set the output voltage. External bootstrap diode if you want to do that. Digital enable. Like I said, you can use a microcontroller to turn it on. They got a little fancy there, but that's okay. Hiccup mode. So when the temperature is over temps, then it will try. Well, I don't think it does that. When it gets too hot, it shuts down. All right, so the hiccup mode should be if there's a short or an overload on the output, then it should go in hiccup mode and try to switch on, and it will switch on once the problem is removed. All right. So thermal characteristics. Now here's kind of a layout thing, because it's a little bit important for noise. So this is what's recommended. And in my latest revision, I tried to follow this as close as I could. And it gives you some notes here. This should be connected by a wide and short trace right here. Keep sensitive components away from this. So you see they have little spaces here. All right. And you want this stuff closest to the device as possible. Close to the device as possible. Keep it away from sensitive components. So they have the ground going around it here. All right. So then it gives you some examples of capacitors that you can use. All right. And then this is the dimension of the chip, so that you can get your Fusion or whatever program PCB layout set properly, the footprint. And that's pretty much it. So that's what we're using. That's the heart of our power supply. Okay. Okay, so there's still a couple more things we got to look at before we finish the video. So first, let's take a look at the input jack size. I almost forgot about that. You got to know what size of jack to put in there so that you can made up a plug to go into the jack so you can get power to it, or it isn't going to work from the very beginning. So yeah, let's check that out real fast. Okay, so here's our power connector. And it has a 2.5 millimeter center pin. I don't know why it doesn't say that here, but it's a 5.5 millimeter barrel size, outside diameter. I don't know why they didn't put that in there. That's pretty weird. But you need to know that when you order the jack to go in there, the plug. All right, so it's rated at 5 amps. It's a right angle. It's one of the very few through-hole parts that are on MainBrain. So this just gives you the specs, and that's pretty much it. It gives you the dimensions so that you can like do your pads and stuff. There's where it shows 5.5. That's the mating jack plug, mating plug. All right. And so some release stuff there. So it's just, that's the PJ-102BH. And I've ran a plug in and out of that thing for years, and I haven't wore one out yet. So it's very durable. I'm happy with it. Okay, and last but definitely not least is the current monitor, the current sense device. So let's take a look at what that is and what it does and wrap this thing up. Okay, so this is our current monitor. It is made by Diodes Incorporated, and it's a low power, high side current monitor. So a high side means that it's on the positive part of the supply of the load. A low side, low side current monitor would be on the ground side of the load. All right, So we're on the high side. So this is our sense. That's that 100 milliohm resistor that we go through to create a voltage drop, just enough. That's the idea, is to create a small voltage drop that doesn't really affect the voltage that gets to the load, just a minimal loss. And so, but enough that you can measure it. So you have this thing, which is pretty much like an op amp type of deal here. And we have this right here. We have the 1107. And so it just creates a voltage divider here, the output. And like I said, that one resistor dictates the ratio here. And then I added a cap, a bypass cap here to ground out high frequency noise. And that's our circuit right there. That's about the only way you can use it, pretty much. They're very sensitive. Now, of all the parts on the board, this thing will get blown out real easily from noise or any kind of too much voltage across these terminals, and it's going to go bye-bye. So this is your regular specs, blah, 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 all that stuff that data sheets have. Some more performance curves, some test circuits, and we're going to test our circuit, and then it gives a description of how it works. And then you can look at this to determine the value of the components that you want to use to get what the range that you want to measure. For like your AD converter might be 0 to 5 volts or -5 to +5 or whatever. So you have to work out on these formulas to get this to work just right. See, they're in this example, they're using 50 milliohms instead of 100, which they'll have half the voltage drop across there, but you're going to be deeper into the noise zone at the same time. And then you have to change this. They have a 5K, and it just depends on how you want to design your circuit. And they even went down to 20 milliohms on this one. So you can look at this. It's not real important unless you're going to design your own. So that's pretty much all the components that we have to go over for the power supply. Okay, so that's how the power supply works. So that's pretty much everything we need to know about it right now. So any other details we'll pick up as we put the parts on the board and do some tests. So that's it for this video, and I will see you in video number 3.